Hey guys, welcome back. We get into a new part of the course which takes a look at the switching aspect of networking. In this particular, we're going to start off by talking about what the switch is all about, how it operates. So let's get started with it. The main topics in this particular video that we're going to be addressing. We're going to take a look at switch functionality. Where does it work? We'll take a look at one of the important components of the switch, which is called the MAC address. Like in routing, you have the routing table. In switching, you have this table known as the MAC address table. We'll talk about how it's built, how the MAC address table is used to forward traffic or data to the appropriate devices. We'll take a look at the switching frame mechanism. How does the switch move the frames within its fabric? And then last but not least, we'll take a look at the actual data packets that are going through your switch environment and then the routing environment, where you have a layer 2 and a layer 3 aspect within the life of a packet. So to get started with, let's go ahead and take a look at what is the functionality of a switch. Where does a switch work at? If you look at this network over here, you have two aspects. You have a local network, which is this guy over here within the building. And then you have the aspect that it connects up to the other networks, which is the function of a router. So the objective of a switch that we discussed as well in the introduction is to connect different devices on the same LAN to each other, whereas the router connects one LAN, one network to another network. All right? So the router operates between networks, between 192.168.1.0 and 12.0, whereas a switch is basically connecting the devices on the same network to each other. Now, you also might have a LAN type environment where you might have multiple small little networks within your building, within your enterprise, within your company. So for example, you might have the sales department, which might be on a different IP subnet or IP network. You might have the marketing department. And this is, I'm not talking about a WAN, I'm talking about a LAN now. If you guys remember from the initial definition of a LAN, it was basically a collection of different networks in the same building, same campus, connecting to each other. And let's say I had a finance department. Now, although they're on the same inside the same building, I might want to segregate them and put them in 3 different networks. So I want to connect them up by using a router, because the router connects different networks to each other. I have the sales, marketing, and finance. Now on the marketing network over here, I would have a separate switch over here. The functionality of this switch over here would be to connect the different devices in the marketing network to each other. They will all belong to the same IP subnet. So all these devices that are connected by a switch all belong to the same IP subnet. The switch in turn connects one port to the router, allowing these PCs the ability to go out of the network using the router as the exit point. Similarly, on the sales side, you would also have a switch, which in turn connects like that. And on the finance side, again, you would have a separate switch which connects like that. So all the devices on the finance department connect up to the finance switch. All the devices on the sales network connect up using the sales switch. Each one of them is a separate IP subnet. And because these are different IP subnets, in order to connect from marketing to sales or finance, I'm going to use the router to connect these different networks to each other. So router basically connects different networks to each other. A switch basically connects the different devices on the same network to each other. Hopefully that part is clear now. Now the other thing that I also want you guys to see is the diagrams. A lot of time you'll see a network depicted like this. You would see a router with a line. This is just the way you represent a network in a diagram. And you would see it like this. This line is not really a wire. It's basically a depiction of that these two these devices, these three devices over here, are on the same network. Now physically they're not going to be connected into a wire like that. Physically, the way it is going to be like this. A router connects into a switch, which in turn will have the PCs connected to each other. So physically it goes like this. And on the other side, again, you would have a switch, which in turn connects up to the PCs like that. So this is your logical diagram. This is more like your physical diagram. Sorry, the other way around. This is your logical diagram, which is your layer 3 diagram, depicting the two layer 3 networks that I have. Doesn't actually show you the wiring. It just shows you a network is connecting all these devices to each other. Here it's actually the wires that are connecting into the switch. And normally on this type of network, on this diagram, which is a physical, you would generally also see ports associated over here. E00, E01, E02. These are the ports on the switch that connect up to the different PCs. E03 on the router side. So again, sorry, not over here. On the switch, this would be your E03. On the router, it's E00 on this side, E01 on this side, which connects up to the switch, which might be E00, E01, and E02, for example, over here. All right? So this is the physical aspect of it. We'll do a lot of that physical to logical mapping in this particular set of videos that deal with the switching aspect. So this is what we've done, or this is what I'm showing you over here, guys, this is an aspect of the physical where I do have my local LAN, which is this guy, connected using these ports. Although I have not shown you the ports on the switch, there would be specific ports on the switch also. This is your layer 3 network that connects the two different sites to each other, but again, internally it again has a switch with multiple PCs on it. So again, on the LAN side, you would have a PC on the inside connecting them to each other. So let's take a look at what the slide has to say about it. The switch connects devices on a single network. Switches forward packets by looking at the layer 2 address of a frame. We haven't talked about that yet. We'll take a look at that in a second. But before that, based on the diagram in the previous slide, the switches connect the PCs within the LAN segment to each other. The switch also allows the PCs to connect to the router. As I showed you over here, this segment is what I'm talking about in that slide. So the router, one interface connects to the same segment, which allows the PCs, if they want to go out, use the router to go out. All right. So we've taken care of this bullet over here. We've taken care of this, and router connects the PCs to other networks. We've taken care of that. Now, the other aspect of the switch is how does it forward traffic? When you want to connect different networks to each other, the router's job is to keep a table that keeps track of all the different networks that you have in your company. So for example, if this is 192.168.1.0, this is 192.168.2.0, these are LAN segments, 192.168.3.0. And then you have segments connecting the different routers to each other, 12.0, and let's say 23.0. This is my network over here. The router will keep a routing table which will keep track of using whatever routing protocol, RIP, EIGRP, OSPF. You looked at different protocols where it would keep track of the connected networks in the routing table. I have two directly connected networks on router 1 and 12, but then it would learn the other networks that are not directly connected to it using a routing protocol, which would allow router 1, whether it's running RIP, EIGRP, OSPF, to learn about the other networks that I have. And let's say via the IP address of router 2. Similarly, I would also know about the 3 network. From his perspective again, via R2, and the third network that I'm not aware of is this guy. And we have gone into detail about the routing aspect in the routing section. Now, the reason I'm bringing it up over here is the router's functionality is to take a look at the packet that is coming in. It will have a source address, let's say it's going from this PC to that PC. Let's say 1.50 going towards 3.50. So the packet is moving from this guy to that guy. The functionality of the router is to take a look at the layer 3 header, see that 3.50 is reachable via this guy, and forward the packet to the next hop. Okay, that's the functionality of a router. It looks at the destination IP address and compares it against the routing table. That is between networks. We've done that already, and we'll take a detailed look at that as well, what happens to the headers. Now, what happens to the traffic within my networks? Now let's expand on that 192.168.1.0 network. I have multiple PCs over here. So I have PC over here, another PC over here, another PC over here. How is data forwarded within the same network? Now let's say I want to go from PC1, whose IP address I'm on the same segment as the other guy, and I want to communicate to PC2 and PC3. So how does that work over here? What do I use to send the traffic from PC1 to PC2? Obviously, the IP address will be there, because most of my protocols are going to be based on IP. So this is the IP packet. Now, in order to forward the packet locally on the same network, the device that will be connecting these PCs to each other is the switch. What the switch does, it takes a look at and works predominantly by looking at the layer 2 header of a device. Each device will have a NIC that connects it to the local switch for Ethernet. The NIC will be assigned a unique address by the vendor. This address is known as the MAC address. MAC is basically from your OSI reference model layer, the data link MAC sublayer. The MAC address is the identifier of that device on the local segment. So when Ethernet communicates, it's going to communicate based on the MAC address locally on the same segment. And what the switch does, it learns the different MAC addresses that are associated with different ports that it has. To keep it simple, let's say this NIC has a MAC address of MAC1. I'll show you what the actual MAC address looks like, but for right now, let's say MAC1, MAC2, and MAC3. What the switch does, as a packet comes in from PC1, it gets forwarded to the switch. Switch receives it on E01 with a source MAC of MAC1. It dynamically learns the MAC address MAC1 came in from port E0/0. That means the device that is connected to E00 on the switch is MAC1. This is called MAC learning. So it remembers that. The next time somebody sends something from PC2, it will learn the MAC address that MAC2 is the MAC address that is coming in from this port E02. Keeps it into a table. And it would also learn that PC3, when it sends a packet, is connected to E01 and its MAC address is MAC3. So when a packet comes in, the switch will not look at the IP address. Its functionality is to forward traffic by looking at the destination MAC address. So if the device is going from MAC1 to MAC2, it's going to consult the MAC address table and forward the traffic by looking at the MAC address. Technically, when you look at this, when you have a packet that has the layer 2 header inside it as well, it is referred to as a frame. So when you talk about traffic getting forwarded through the switch forwards frames. Once the router receives it, it strips the layer 2 off and it will take a look at the IP address and forward the packet based on IP addresses. That is called a packet. So when you have just the layer 3 and above, it's called a packet. When you have layer 2 and layer 3, it's called a frame. So the switches are focusing on the frame aspect, and they will forward the traffic by looking at the layer 2 header, which has the MAC address. And that's what this slide over here is talking about. The switch forwards packets using a layer 2 header or address known as of a frame, hence are generally referred to as layer 2 devices because it's forwarding by looking at layer 2 addresses. The layer 2 address of a device on an Ethernet segment is called the media access control or the MAC address. Where do I get the MAC address? It's the address that's etched on, burnt in onto your NIC, your network interface card, by the vendor. And the next slide, we actually take a look at what the MAC address looks like. So basic thing from here that we understood on the slide is that the switch is the device that connects the local segment to each other. The switch will forward traffic based on the MAC address, which is the address on the NIC. All right. Now, what is this MAC address? Let's take a look at this MAC address in a little bit more detail. The MAC address is a unique identifier for that NIC. Now, to make sure that that NIC is a unique address, the way it is done by a committee that is responsible for assigning or keeping track of unique MAC addresses. Just like the IANA is responsible for IP addresses, the IEEE committee is responsible to assign different vendors, maybe 3Com, maybe Intel, maybe Cisco, what is known as a organizationally unique address. So every organization will have a 6 hex digit, which equates to 4 bits. IEEE assigns that particular vendor a unique identifier for the company. It is in hex, it's 6 hex digits, and based on our earlier conversion from hex to binary, we know that 6 hex digits, each hex digit equates to 4 bits, which gives you a total of 24 bits. That is the aspect of the MAC address that is assigned by IEEE. All right. So for example, what I've done over here is I've basically shown you that the IEEE has assigned this particular vendor a unique identifier for the company, which is 0001.A, 2 A's, right? 6 digits. Now, it is now the responsibility of the vendor, whether it's Cisco, Intel, 3Com, to make sure when it manufactures all the NICs that each NIC has a unique identifier. The responsibility of the company, let's say Cisco, which has been assigned, let's say, this unique what? Vendor ID. It's the responsibility of Cisco to make sure now when it manufactures the NICs, the last 24 bits, again, 6 hex digits, is unique within the organization. So Cisco makes sure that they make this part a unique identifier so 2 NICs don't have the same MAC address. IEEE is responsible for the first 6 hex digits. Cisco is responsible for the next 6 hex digits. So the total number of hex digits that you have for a MAC address is 12. Okay, so a MAC address consists of 12 hex digits, and again, as I said, each 12 hex digit equates to 4 bits. So if you want to do it based on bits, it's a total of 48 bits. That's the size of a MAC address. Or you can say 6 hex digits. That's another way of saying it. Out of this, 12 hex digits. Out of the 12 hex digits is broken down into 2 parts. The vendor ID, called the OUI, organizationally unique identifier, which I call the vendor ID because it's the ID for the vendor. And the next 6 hex digits are the unique identifier for the interface manufactured by the vendor. And the way it's written, different vendors write it differently. Bottom line is it'll be a 12 hex digit number. Some vendors like Cisco, if you do show interface brief, you'll see the number listed like this: 0001.AA00.0001. You look at other vendors, you might see the same 12 hex digits, but they're written in 2 hex digits separated by a colon, 2 hex digits, colon, 2 hex digits, colon, so on and so forth. Total number of hex digits is still 12. The third way, this is a common way you'll see it in the Windows PCs. The separator over here is a dash, 2 dash, 2 dash, 2 dash, and so on. So either way you look at it, the first 6 hex digits is your organizationally unique identifier, the vendor ID, and the last 6 hex digits in that MAC address is the unique identifier assigned by the vendor to that particular interface. And this is the address that is used by the switch to forward traffic within the company. Now, within the network, actually, not the company. Within that layer 3 network, the layer 2 switch will do that forwarding over here. So let's take a look at an example over here. If I have a switch down here, on this switch, I have 3 PCs connected. Each one has its own MAC address, 0001.11.11AA. What do you find out when you look at these MAC addresses? You see that all these MAC addresses are coming from the same vendor. How do I know that? If you take a look at the first 6 hex digits over here, of all the NICs, they are the same. That means they're all coming from the same vendor and their unique identifier 11AAAA, 11BBBB, 11CCCC. And I also have the layer 3 aspect, which is the IP address, because I'm connected to the same switch, same LAN, same network. They all belong to the same common network, 192.168. I'm assuming it's /24. All right, .51, .52, .53, 3 IP addresses on the same subnet connected via a switch. And what I'm not showing you over here is that switch generally would also have a connection to the router. So if these PCs want to go out, they would use a router to send the traffic out. All right. Now, once I'm done with this, the next thing I want to show you guys over here, now that you've seen the diagram, let's take a look at the MAC address and how the MAC address is built. So let me do it over here for you guys, and then we'll go through the slide. Let's say this PC wants to communicate to this PC, or for that matter, it wants to communicate to the internet. It will send a packet out. When it sends a packet out, let's say PC1 is going to PC2. At layer 2, the frame will look like this, and then it'll have the IP header. Source IP, whatever it is, destination IP, whatever it is. When this packet comes in, this frame comes into switch 1. Switch 1 receives this frame. It doesn't care about the destination at this point. It cares about the source. It takes a look at the source and sees if this source is already known to me or not. Because I'm just bringing these devices up, the switch at this time would not know where this MAC address is coming from, but it received the packet coming in from E00 with a source address of MAC1. That tells the switch, hey, listen, I've received a frame that has a source MAC address of MAC1, came in from E00. That tells me if I in the future need to communicate to whom? MAC1, it should be on port E01. So it starts building your MAC address table automatically. And in this table, what does it keep? It keeps the MAC address, which in our case was 0001.11.11 AAA, and assigns it to a interface on the switch E00. Similarly, when PC2 sends a packet out, it would have a source MAC of 0001.11.11 BBBB, and let's say it's going to this MAC. I'll just say PC1 MAC. When the packet is received or the frame is received, the switch takes a look at the source first, says, I don't know about 0001, 1111, BBBB. Let me add it to my MAC address table. And I received this frame from E02, so I should keep it as E02. And then it looks at the destination, sees the destination address is 0001, 1111, AAA. I know that it's connected to E02, so it forwards it over here. So PC3 is not involved in this communication, does not receive the frame when PC2 wants to talk to PC1 because of the MAC address table that is built dynamically or automatically on what? On switch 1. Similarly, when PC3 initially sends a packet out or a frame out, it would also, the switch would also learn that I have a MAC address 0001, 1111, CCCC, which is connected to E01, puts it in the MAC address table. So anytime a packet or a frame is received where? On a switch port, it checks the source and makes sure that source is in my MAC address table because the source is coming in from a particular port. That is the way the switch learns the MAC address. So as soon as a frame is forwarded into the switch looks at the source MAC, figures out that this MAC address is attached to this particular port. So it learns it and puts it in the MAC address table and uses the MAC address table to forward traffic for future frames. So let's take a look at this process over here. I've documented that process for you guys here in the switching frame table, MAC address table actually first. The switch builds and maintains a table known as a MAC address table using an automatic process known as MAC learning. I just went through that. The MAC address table associated with this associates, it should be associates, the switch port with a specific MAC address connected to that port. So as soon as a frame comes in, which has a source MAC of 0001, 1111, and the switch receives this frame from E0, let's say 0, it would put in the MAC address saying that I've learned this MAC address from E00. The switch learns the MAC address to port assignment by analyzing the what address, what part of the address? The source MAC address of the frame. If a frame comes in with a MAC address it is not aware of from a port, it will learn it and store it in the MAC address table. The switch learns the topology of the network using this methodology. So by doing this, I'll eventually learn about all the different devices that are connected to the switch. The switch will forward the frame by analyzing the destination MAC address. It will only forward the frame to the associated port with the MAC address. If the MAC address is not known, it is going to flood the frame. So for example, initially when the MAC address table does not have all the MAC addresses learned and a frame comes in into the switch, it is coming in from 0001, 1111, AAAA. It's going towards, let's say, 11111, BBBB, and the IP addresses, source and destination IP. When the switch receives the frame, it looks at the source MAC. It's the first frame coming into the switch. It looks at the source MAC came in from E00. It will build the MAC address table or start building it. Looks at the destination. It doesn't see this in my MAC address table at this point. So at that point, the first time around, it is going to flood that frame to all the ports. Why? It's an unknown destination. PC2 receives it, he needs to respond back. Now the source becomes a destination, destination becomes a source. So the return packet looks like this. Source is 0001, 1111, BBBB. Destination is 0001, 1111, AAAA. And the source and destination IP. When this frame is received on switch 1, again, it checks the source. I don't know about this guy, so I'll put it in my MAC address table, auto learn it. The frame was received from E02. The destination now says, oh, I know where it's at. sorry, I know where the destination is at. It's on E02. So the second frame, the return frame, is not getting forwarded to PC3. It just goes to this guy. So now on the return, it's not going to go to PC3 because I know the destination address. So the switch will only forward the frames to known ports if I know the MAC address. If I don't know it, I'm going to flood it. And that's what this statement over here is talking about. It will only forward the frame to the associated port with that MAC address. If the MAC address is not known because it hasn't communicated yet, it'll flood it to all ports on the switch. All broadcast and multicast frames are always flooded because broadcast and multicast is meant for a group of devices. All right. Now, the basic example that I just went through, I've just documented that for you guys as well. So if you want to go back and read it, let's assume the switch does not have any MAC addresses in the MAC address table. PC1 wants to communicate to PC2. The switch will receive the frame from PC1 on Ethernet 0/0. The switch will analyze the source MAC address of the frame. It'll store the MAC address. So that's where it would have created the MAC address entry for PC1 off of E0/0. The switch will now check the destination MAC address against the MAC address table. As I said, there is no MAC addresses. PC2, the MAC address, as the MAC address is not in the MAC address table, the switch will flood it to all ports. So this time around, it's flooding it. So everyone receives it. But in a minute, when PC2 will receive the frame, it will respond back. When it responds back, it will put its source MAC address as 0001, 1111, BBBB, and send it back. The switch will receive it on the port that was connected towards PC2, which is E0/2, and store this MAC address over here. The switch will learn the new MAC address and store in the MAC address table. Switch will only forward the frame on port E00 as it has already learned the MAC address in the initial communication. So once this is done, this is just the initial part. Once this is done, switch believes in forwarding packets or frames only to the ports where the destination resides at. So it doesn't unnecessarily flood the entire network. That's the difference between a hub and a switch. All right. And in the next slide, I actually show you that MAC address that I've been writing for you. The switch will learn all the MAC addresses on the network by using the same mechanism. Switch will use the MAC address table to forward frames to the specific destination ports. So this is what eventually your MAC address table based on this topology will look like. Okay. And now if this guy wants to talk to that guy, the destination MAC address will be 0001, 1111, BBBB. When the switch receives it, it knows BBBB is on E02. So that communication, once the MAC address table is built, is direct from PC1 to PC2. Understood? So that's communication within your switching environment. Now, if you take a look at your initial screen, what we have covered so far is the switch functionality, that it works within the network, whereas a router connects different networks. It is forwarding traffic based on the MAC address of the device. MAC address is that 12 hex digit number assigned by your vendor. The vendor gets the first 6 hex digits from where? IEEE, which is called the organizationally unique identifier, which I refer to as the vendor ID, and then you have the unique identifier for the device. This is the responsibility of the vendor to make sure that the unique ID is unique. Now, we also took a look at how the MAC address table is the one that is used by the switch to forward the frames to the appropriate devices, and how it learns and creates a MAC address table. We also went through it. Once we learned the MAC address table, how the switching took place, we've also gone through it. Now, I want you guys to take it to the next level. At this point in this video, I've just focused on the layer 2 aspect. Now what I'm going to do is I'm going to take a look at how communication works in a IP network within the same network where you have a switched environment involved, but I'm going to take it to layer 3 now as well. How does PC1 create that frame that knows about the MAC address of the remote destination? And that's where the protocol ARP comes into the picture. So in order to communicate within a single network, the PC will need to identify the destination device by specifying not only the destination IP address, but also the MAC address. So I know I need to communicate to 192.168.1.51, but I don't know the MAC address for 192.168.1.1. So how do I find that out? It is done automatically by the PC using a process known as address resolution protocol. It's a layer 2 protocol. The responsibility of ARP is to discover what? Discover MAC addresses for specific IP addresses. All right, let's take the network in the previous slide as an example and take a look at the IP communication. So what I want to do is I want PC1 to talk to PC2. Let's see the process that takes place for this PC over here, which has a MAC address of 0001.1111 AAA with an IP address of 192.168.1.51. It wants to communicate and send a packet to PC2, whose MAC address is 0001.1111 BBBB with a destination IP address of 192.168.1.52. What is the process? What are the steps? I'm going to take you through it one step at a time. So the first step, PC1 wants to communicate at layer 3 from this address, which is my source address, to this particular destination address. All right, I've gotten this address through name resolution, DNS. I know that I want to communicate to that particular device. So I create my layer 3 header. This is your layer 3 header. What does it contain? It contains the source IP as 192.168.1.51, destination IP of 192.168.1.52, and the actual data that needs to be sent. But now when I need to forward it to the switch, I cannot forward this packet like this. Why? The switch does not look at the IP address. It looks at the MAC address. So I need to figure out what is the MAC address for this guy. And that's where that protocol that I talked about called the ARP is used to discover what? The destination MAC address. How does it do it? It sends a ARP packet, which is known as an ARP request. In which it's going to say something like that. My source MAC address is 0001.1111 AAAA. I'm sending it, I don't know the MAC address, so I'm sending it to this special address which has all F's in the 12 hex digits. This is a special reserved address for broadcasting on that particular segment. So if I want to send a packet to everyone, this is the broadcast MAC address. So all F's in the destination MAC address basically is telling me that it is a broadcast address. And in that packet, the data portion of ARP says, what is the MAC address for 192.168.1.52? Okay. When the switch receives this frame, it looks at the destination, MAC address, it says broadcast. So send it to everyone. So what the switch does, if I go back over here, the switch will take it because the destination is what? Broadcast. It's going to forward it here and it's going to forward it here. PC2 and PC3 receive it. And what did they receive? They receive somebody is asking or looking for what? What is the MAC address for 52? PC3 ignores it. It's not his IP address, but PC2 says, oh, somebody is looking for my MAC address. And what does PC2 do with it? PC2 responds back. The ARP broadcast is sent to all devices on the switched environment. PC2 receives it, receives the broadcast, and responds back to the ARP request with its MAC address. This is called a ARP response or reply. Okay, in there I'll put my MAC address destination because I know the request came in from 0001.1111 AAA. I'm going to send it back to him. Say MAC for me, or 192.168.1.1 is 0001.111 BBBB. Once PC receives it over here. The PC over here on the device will receive this frame where PC2 is saying the MAC address for 192.168.1.52 is this MAC address. PC1 over here creates a table known as the ARP cache. So it doesn't need to keep on doing this on a frequent basis. In there, it maps over the destination IP address to the corresponding MAC address. So once it finds it, puts it in the ARP cache. Once it's inside the ARP cache, what's next? PC1 receives the ARP reply and stores the MAC address of 192.168.1.12 or 1.52 in the local ARP cache. The next time it needs to communicate to the same IP, it does not need to send an ARP request. Why? I already know that if I want to reach 192.168.1.52, the MAC address is 0001.1111 BBBB. All right. Similarly, it'll do the same thing for PC3. So this guy over here is PC3. The other devices will do the same to build the ARP cache using the ARP broadcast. So ARP request, the broadcast packet, will be used on a need basis to build your ARP cache, which is built on each one of those devices. So right now, once everybody has communicated at least once to each other, you are going to see an ARP cache over here, which is going to say if I want to reach 1.52, sorry, my destination MAC address has to be, similarly, I'm going to have an entry for 53 with the associated MAC address. So this is the ARP cache of PC1. PC3 will build a similar type of ARP cache, not for its own address. It generally will use it for 51. And another entry for 52, which will be, and the third PC or PC2 will also have an ARP cache which would say if I want to reach 11, the MAC address I want to send it to is this guy. If I want to reach, all done dynamically. Hope you guys are clear with that. So this, once PC1, PC2, PC3 has it, I don't need to keep on sending ARP requests. So this is just the initial part. When the network comes up, they're discovering the MAC address for each and every associated IP address that they need to communicate to. And this is what the ARP cache is looking like on PC1. So once that's built up, let's go back to that original packet that I was trying to create. I had the layer 3 header created. The whole process of building this ARP cache was so I can put the layer 2 header on it. And that's the next thing. Once I have the ARP cache built, now what I'm going to do over here is I'm going to use that to do what? I'm going to use the source MAC as my MAC. Destination MAC, I just discovered that using the ARP request. Source IP, destination IP. When I send this packet, I'll forward this packet to whom? This packet will be forwarded, or this frame will be forwarded to whom? To the switch. The switch would automatically know that this destination MAC address, because again, MAC learning has taken place already, if you remember, is connected to E0/2 on the switch. It will only forward it to that port. He receives it, he will respond back. So I'm just looking at the destination MAC address at that time to forward it. So the switch will forward the packet based on the destination MAC address. And that's how IP communication works within my same network. All right. This is what was happening when PC1, PC2, and PC3 were communicating. In this case, the three PCs were located where? In the same IP subnet. All right? So that's how the layer 2 and a layer 3 header is built. And this is what a full frame will look like. That includes the source MAC, destination MAC of the two PCs, source IP, destination IP of the PCs, and the data. All right, this is within the same IP subnet. If you take a look at the two networks over here, you will notice that these two networks, these two devices, source and destination, happen to be on the same network. So this source MAC is the PC's MAC, this destination MAC is the second PC's MAC. All right, things change when communication works between networks. So let's take a look at this as an example in terms of how does communication work, where I have a local switch over here. I'm not showing it to you over here, but let's say there's a switch 1 over here, switch 2, switch 3. So switch 1 will have PC1 connected to it and R1's E01 connected to it. PC2 has, sorry, switch 2 has PC2 and R2 E02 connected to it. Switch 3 has should be PC3 and R3 LAN interface connected to it. And it would have its own local MAC address table. In this MAC address table, I would have the PC MAC and I would have the R1 MAC. This MAC address table over here would have PC2 and R2 MAC. This switch will have, or the switch 3 will have PC3 and R3 MAC. Now each MAC address on R1 would be different. So to be very specific, R1 E1's MAC address will be over here. Good so far? So this is what my network looks like. Now my objective to show you how IP communications work in the routed environment in terms of what happens to layer 2. This is critical because this is how a packet lives through a internetwork, which is connecting different networks to each other. Okay, my objective over here is to communicate between PC1 and PC3 over here. Okay, so the source address will be, and that never changes, the original source will be 192.168.1.50, and I want to communicate to 192.168.3.50. That's my source and destination. Now, when I live within my same network, I would do an ARP to figure out the destination IP. But what happens though is before I do the ARP for the destination IP, there's a process that is run on the PC to determine if the source IP and the destination IP are on the same network or different networks. If they're on the same network, well, I'll go ahead and I need to look at my layer 2 locally. So I need to find out the MAC address for that destination. But if they're not on the same network, I cannot communicate from PC1 to PC2 using the MAC address because the MAC address is only within my own local switched environment. That's where it works. This switch over here would not have any idea about the MAC address of PC3. So what happens is it does a process to figure out, which is called the ANDing process, that my source and destination are what? On different networks. If they're on different networks, the PC needs to be configured with the IP address or what is known as the default gateway. So PC1 needs to know if I want to communicate to a device that is not on my network, who do I send the traffic to? In my case, my default gateway is going to be 192.168.1. Let's say 1. So once I know that my default gateway is 192.168.1.1 and I need to communicate to a device that's not on my network, my ARP will not go for what? PC3, the destination. I'm going to send an ARP looking for the MAC address of the default gateway. If I have it in my ARP cache, good enough. I don't even need to send the ARP request. But if I don't have the MAC address for this guy, in my ARP cache, I'll figure out the MAC address for R1 by sending an ARP request on this local segment. R1 will respond back and say, hey, my MAC address is MAC R1. And based on that, PC1 will create a frame which will have the source MAC address as MAC for PC1, which is the 0001 1111 AAAA. Destination MAC will not be the MAC for the destination device because this destination is on a different network. It will be for R1. I'll send it to my switch. Switch will forward the packet or the frame to R1. R1 receives it. R1 says, oh, this is a frame that is meant for me. Strips off the layer 2, and when it sees inside, it sees, oh, this is meant for some other network, 3 network, and it goes through the routing process. Now to depict that, show you that, let's take a look at the IP communication in the routed environment. In order to communicate between different networks, the PC will need to identify the destination device by specifying the destination MAC address and destination IP address as well. So in my case, I would have put in source of 1.50, 3.50, 2 different networks. As the source and destination devices are on different networks, a router will be used to connect the networks. How do I know that? It goes through the ANDing process. It figures out my network is 192.168.1, the first 24 bits. This is on a different network. So once basically I have figured out that they're on 2 different networks, I'm going to do the ANDing process to figure that out. Once I figure out they're on different networks, I'm going to start the ARP not for this address. I'll send the ARP for my default gateway if it is not already in my cache. And let's take a look at the life of a packet as it goes through a routed environment. So let's go through it one step at a time. PC1 checks the source and destination address and finds the destination device is on a different network. PC1 will need to use the configured default gateway to reach this address. But it doesn't change the destination IP address. If you take a look at the destination IP address, it will still be what? The original source and the original destination. The way it communicates to the default gateway is by using the layer 2 communication, which is the MAC address. All right, the PC uses a local address in layer 2 header and the original source IP and destination IP address in the layer 3 header. It will either check the ARP cache or send an ARP request. ARP request for whom? My default gateway. So let's say my default gateway was 192.168.1.1. It's going to send an ARP request saying who is with a source MAC of, just like we did for the destination PC, with a destination MAC address of all Fs. R1 will receive it. He will respond back with his MAC address. The PC will keep it in the ARP cache. So once the PC has it in the ARP cache, for future communications, I don't need to do the ARP request again. And based on that, I'll build my frame. Take a look at my frame carefully. What does it say? Source address, I'm using my MAC address. Destination address is not the MAC address of 3.50. It is the MAC address for R1 MAC. At layer 3, source IP, destination IP, or the original source and the original destination. That doesn't change. The local switch will forward the packet to the default gateway. When the packet or the frame is received by the local switch. Where's the local switch again? Over here. This is the local switch over here, which would have 0001 1111 AAAA on this port. Let's say this is port E00. And similarly, you'll have the MAC address for R1, whatever that is. Let's say on E01, which is this guy. So it'll receive it with the destination MAC address of MAC1, forward it to R1. R1 receives this frame. The first thing R1 will do, R1 will first of all strip off the layer 2. Okay? So what it does, it says, oh, this frame was meant for what? For me, it will take this part of the header and strip it. Once it strips it, it then looks at the destination IP addresses. Oh, it's not meant for me. it's meant for someone else. Okay? The router will check its routing table to figure out the next hop. To reach 192.168.3.0 network, the next hop is R2. Now R1 will send an ARP or look at the ARP cache to figure out the MAC address for R2. That's what I'm saying over here. It'll find the MAC address of R2 in ARP cache or use the ARP request to discover R2's MAC address. It will recreate the layer 2 header. This is called a layer 2 rewrite, in which now the MAC address is R1 MAC, destination is R2 MAC, the source destination IP doesn't change. R2 will receive the packet, it will strip the layer 2 header off. So again, just like R1 stripped it off, R2 will strip the layer 2 header off. It will also check its routing table once this is gone. It checks the routing table, says 3. Oh, 3 is reachable via R2. So it'll say then find the next hop address for 3.0 in the routing table. The next hop would be R3. R2 will rewrite the layer 2 header using its as a source MAC, destination MAC. So what's happening to this packet, the life of a packet, as it traverses through this network? Over here, the source MAC is what? PC1, destination MAC is R1. Source IP does not change. This doesn't change. This is the way the packet is received on R1. R1 receives the frame. The first thing it does, it takes the blue part out, the PC1 R1 MAC, looks at the routing table. The routing table would tell it if it wants to reach 192.168.3.0. The next hop is 192.168.12.2. So now R1 will check the MAC address for 192.168.12.2. Either in the ARP cache or send a request. R2's MAC address will be found. This is where R1 will rewrite the header, and it looks like this now. R1 MAC going to R2 MAC. Source IP and destination IP remain the same. So I'll just say 1.50 and 3.50. That didn't change. Sends it over to whom? This guy. He again, first thing it does, he strips off the layer 2 header. Okay. Finds out 3.50. How do I reach 3.50 over here in the routing table? His routing table will say 192.168.3.0 is reachable via 23.3, which is this guy. Says, oh, I need to find the MAC address for 23.3. Checks the ARP cache or does an ARP request. Figures out that the MAC address for, I can just create it over here now. The MAC address for R3 is whatever it was. So over here I'll put R2 MAC as a source, R3 MAC as the destination, still 150 and 350. That doesn't change. This part is unchanged. R3 receives it. He strips the layer 2 off. He sees that 3.0 is directly connected on E01, so it knows it's over here somewhere. He sends an ARP for what? 3.50. He will respond back. Now on this last leg, the frame will look like this. R3 MAC, this guy over here, sending it to 0001, 1111, CCCC. Source is 1.50, destination is 3.50. So that never changes. Source IP, destination IP remain the same. What kept on changing in the frame is what? The layer 2 header. So every segment would have a different layer 2 header, eventually gets it to PC3 over here. And that's what I have written for you guys over here. The documentation over here talks about that. Router will check its routing table to figure out the next hop, reach 192.168.3.0. The next stop would be R2. R1 will use R2's MAC address to forward the packet, again doing an ARP cache check or doing a request to discover R2's MAC address. It'll recreate the layer 2 header. So between R1 and R2, this is what the frame looks like. R2 receives it, again does a check in what? The routing table to find where 3.0 is. From the perspective of R2, the next stop is R3. R2 will again do a ARP cache or ARP request to figure out the MAC address for R3, finds it, rewrites the MAC layer 2 header, R2 MAC as the source, R3 MAC as the destination, source IP and destination IP, always the same. Forwards it to R3. Now once R3 receives it, R3 is the router that is directly connected to the end device. R3 receives the frame. It will also strip off the layer 2 header. It will check its routing table to find that the 3 network is directly connected on E01. It will use the ARP cache or ARP request to figure out 3.50, finds it. R3 will rewrite the header from R3 MAC to the destination MAC of 0001 1111 CCCC, which is the MAC address for PC3. And I'll forward the packet there. The local switch will use the MAC address to forward the packet to PC3. Once PC3 receives the packet, the PC will respond back. And that's how the packet, the frame looks like as it travels through a routed network. So as you guys can see, in a routed network, every segment that you have, the layer 2 is rewritten, where the forwarding of the packet is done based on layer 2. The source layer 3, destination layer 3 is unchanged as the packet traverses through an IP network, a routed network. All right. So to recap, what are the different things that we learned over here, which was very important from the perspective of the switching section? This is your foundation. We figured out where the switch works. Switch is a device that works within the network. All right. So switch connects the different devices on the same network to each other. The router connects the different networks to each other. So the switch works within the network. It is generally to connect different devices to each other on the same segment. You might have multiple switches on the same building because you might have 2 different networks, like the example that I gave you for sales, marketing, and finance. We also learned that forwarding of packets or frames inside the switch environment is done by the layer 2 header, and the layer 2 header, the address that it uses is called the MAC address. This is your layer 2 header. And the switch will forward your frames by looking at the layer 2 address. The forwarding is done based on this. We also learned about the MAC address, how it's derived or how it's assigned. It's assigned by IEEE, the first 6 hex digits to the vendor. The vendor then in turn adds another 6 hex digits, making it a 12 hex digit number, which is then assigned to the actual NIC, the actual interface. The MAC address table, how it was built, we learned that it is built dynamically and automatically by looking at the source address of an incoming packet, checks the source MAC and the corresponding port that the source MAC came in from, and builds a MAC address table. On a switch, the packets are forwarded by looking at the MAC address table, the destination address, and the corresponding port. So on a switch, the frames are not forwarded to all the ports, only to specific ports. Although initially when the packets or the frames come in, the switch is not aware of all the MAC addresses, so a destination comes in, which I'm not aware of. I'm going to flood it to all the different ports until I learn the MAC address. We also took a look at how IP communication works in a switched environment. Just to recap, in a switched environment, that means within the network, my ARP, my layer 2 will be the MAC address for the final destination, final device. This is over here. And for a routed network, when I do an ARP, I will always do an ARP for what? The default gateway. The layer 2 is the one that keeps on changing between segments until it gets to the final destination. So ARP in the local segment is done for the default gateway or the next hop until it gets to the final leg, and the final leg it'll do the ARP for the final destination. So in our case over here, if you remember the last thing that we discussed in the routed environment, ARP on this segment was for what? Default gateway. ARP over here for the next hop. ARP over here was again for the next hop, and over here it was for the destination device. The MAC address over here on this segment, PC1 to R1, the MAC. The IP is always going to be from where to where? The original source to original destination. Here, the layer 2 or the MAC header would be R1 going to R2. Over here, it would be R2 to R3. The IP, as I said, remains the same. In the final one, it will be from R3 to PC3. This is PC3 over here. I'll change it. All right. Very important video. Go through it. If you have any doubts about it, I want you guys to be completely clear with this. This is essential for you guys to build a good foundational knowledge of how traffic works in a local network and how it works in an inter-network, which you connect different networks to each other. Thanks for watching. I'll see you guys in the next video.